Okay, Hari, over to you.
Yes. So hello everyone. So today I'm going to give a presentation on Intel Data Direct IO technology or Intel DDIO. So first we will discuss what are the requirements or why this technology is required, then how it works, and what are the advantages which we get using Intel DDIO, and what are some of the performance issues or the areas which still needs to be addressed and can be researched on. Start. So let's look at the trends in network virtualization. So using the techniques such as software-defined networking and network function virtualization, we are now capable of virtualizing the network capabilities. For example, earlier we have load balancer firewalls as dedicated proprietary hardware boxes. Now we have software-based load balancer and firewalls, which are running on shared general purpose servers. This is coupled with demand for high bandwidth applications such as video streaming, IoT, and the advent of 5G technologies. So now this movement of applications which require high-speed network I/O from the dedicated hardware to software-based network functions have shifted the focus of providing high throughput, low latency, and service time guarantees from the dedicated hardware boxes to software. So basically, we have to provide the predictability. So this is coupled with the rise in Ethernet speeds or link speeds. So here we can see a figure from Ethernet Alliance roadmap. So we can see the network speeds are increasing at a tremendous rate. The result of this is that we have a shorter time, shorter packet inter arrival time. So we for example, if I have a 64 byte packet arriving at 100 Gbps, so I only have a time of around 5.12 nanoseconds before the next packet arrives. So this has mandated a tight bound on the network processing time. So these software-based network functions are thus not able to match the performance of as provided by the hardware. So overall, if we see some of the performance issues in NFV workloads or the this network function workloads are how to keep up with the demand of high bandwidth and increasing link speeds because we have a lesser time to process the packet. So somehow we have to optimize the packet processing to achieve higher throughput. Then we have how to provide the service time guarantees. So basically, we have to provide predictable performance as provided by the hardware and how to ensure performance isolation. So NFV workloads means that these multiple software applications are running on a shared general purpose server, and it may happen that the performance of one application got degraded due to interference caused by some other application. So how to ensure performance isolation? So this is a result of experiment carried out in this paper. So here they have plotted the degradation in throughput and latency when this application was run in a shared environment in comparison to it was being run in an isolated environment. So here we can see that some applications have faced a degradation of about 35 to 40% in. So this is evident that when we run multiple network functions in a shared environment, the performance degrades, and somehow we have to find a solution to so that optimum performance we can get from every application. So before proceeding further, let's briefly see how the network IO or the network packet processing happens. So whenever an application has to transmit the data, it will use the open close or read write socket system calls to request the kernel to send the packet. Then the kernel will process the packet and add the relevant headers in the buffers available with the socket which is attached to the application. So these are basically socket buffers for every application. So the data and the headers will be stored here. Now, whenever this packet processing is complete, then the kernel will pick up this packet and store it into the TX ring of the network driver, which means that packet is ready to be sent. And whenever the NIC or the physical link is ready to transmit the packet, it will pick up this packet and send it over the physical media. Similarly, in the RX path, whenever the packet arrives at the NIC, it will DMA the packet into the location which is pointed by the TX RX ring and raise an interrupt. So whenever the CPU will come to know that okay, packet has arrived, it will take the packet, store it into the buffers, and here it will do the packet processing. It will strip the headers and take out the payload, and then it will copy the payload into the application. So this is general overview of how in detail. It is a very long story, but just in the high level overview. So some of the overheads are switching from user mode to kernel mode. So this mode switching requires considerable time, and it has many after effects. Then multiple copying of packets is involved. For example, from NIC to buffers, and from buffers to the application memory. And this multiple copying packets has to be done for every packet. Then interrupt processing is involved. Some of the software-based solutions which have been proposed and implemented are kernel bypass techniques like DPTK, where we bypass the kernel itself, and this packet processing is implemented in the user space. And then a new API which reduces the interrupt load, and we can do received side scaling at NIC, where instead of only one TX and RX ring, we can have multiple TX and RX rings, and the incoming packets can be distributed among multiple cores. These are some of the optimizations proposed and implemented. Now, what is the role of memory access speeds? This is traditional memory hierarchy. So where when we go down, the access takes a lot of time. So why it is important is that these buffers and the network driver TX and RS rings, these are frequently accessed when we need to process the packet. So somehow if we can maintain these data structures in the cache, then we can access them at a faster rate, and we can optimize the performance. And let's see about the Intel processor and core resources. So traditional, we have a multiple sockets in a server, and each socket we have multiple cores. So in each core we have a private L1 and L2 cache, but a number of resources such as last level cache, integrated memory controller. These resources are shared among multiple cores. So due to this sharing of uncore resources, as you call it, there is a contention for these resources, which leads to performance degradation, because even if we run different applications on different cores, but they will contend for these shared resources like LLC and IO memory controller, due to which the performance will get degraded. So till now we have seen some of the software-based optimization. Now Intel Data Direct IO technology is oriented towards network IO, and it's a microarchitecture level optimization technique. This technique is specifically aimed towards applications which are involved in doing network IO processing, like sending and receiving network IO packets. It was introduced with the Intel Xeon processor E5 or Haswell CPU, and it enables faster IO data transfers that requires fewer trips to memory. So basically what it does is it makes the processor cache the primary destination of data rather than the main memory. I will explain it in coming slide. So traditionally what happens, as we have seen earlier also, that this is simple block diagram. So whenever a network packet arrives at the NIC, it will DMA the packet into the DRAM using direct memory access. The packet will be sent to the DRAM, and whenever CPU wants to process the packet will be brought back to the cache. So what is the disadvantage of this is that it requires multiple memory accesses, like a memory write and a memory read. So due to this, my access latency is increased because because of accessing the DRAM, and it will also increase the memory bandwidth utilization, because for every packet this path I have to follow. So this is inefficient. So with Intel DDIO, what Intel has done is that the NIC will directly write the incoming packet into the last level cache itself. It will not go to the DRAM. The incoming packet will go directly into the last level cache, from where the CPU will process the data. So what is the advantage is that it reduces the latency, because now I can access the data directly from cache at a faster rate, and my memory bandwidth requirements will also reduce, because the multiple round trips from DRAM to cache will be reduced. Some of the characteristics of Intel DDIO. So by default, only two LLC ways are reserved. So we know that a number of LLC ways are there in cache. For example, in Skylake it's 11, in as well it was 20. So two LLC ways are reserved for DDIO. So the DDIO, or basically the application which is doing the network IO, they can use only two LLC ways. However, the other applications or the cores that can write to the these two LLC ways. So basically what I meant to say is that these are not specifically reserved for DDIO. Only limitation is that DDIO can write to these two LLC ways. And these cannot be partitioned using CAT. So we know that in using Intel cache allocation technology, we can divide the cache into multiple applications. But if a number of network IO applications are there, they will all share the two LLC ways. This cannot be partitioned using CAT. And if this limit is exceeded, so we have a limited space of two LLC ways. So somehow if my incoming packet fill this two LLC ways, then for making space for new IO data, the existing IO data will be evicted to DRAM. And this is a transparent technology. It does not require any changes to driver applications or OS. So now let's look into more detail of how an IO read or a network transmission happens with Intel DDIO and without
Hari,
Intel DDIO. Yes.
Hari, I have some doubt. Will you take it at the end, or is it fine to ask you now?
Okay, you can ask.
Okay, yeah. In the previous slide, when you mentioned about CAT. So you mentioned that DDIO. You mentioned that these two ways are not always. Reserved for DDIO. Something like that you mentioned, right? What did you mean by that?
Basically, suppose I am having 20 LLC ways. So and I have 5 application. Which means that if I am having like out of 20, the 90th, 19 and 20th way I am using for DDIO. So when the NIC will write the packet, it is restricted that NIC can write the packet only in the 19 and 20th LLC way. But it's not the other way around. Whenever any application has to write the packet in the cache, it is free to use the 19th and 20th LLC. That's so the NIC is restricted to use only limited LLC ways, but the cores can write to any LLC ways. This is
okay. I got your point. So is like that course data can evict this network. So this IO data.
Yes.
It can always be the case, or it can be the other way around also, right? In those two LLC ways.
Yeah. There is one problem we call latent contender problem. I will explain in one slide. This is specifically due to this issue that core can evict IO or IO can evict core data.
Okay. Yeah, I got you. I got the answer to my question. Thank you.
So traditionally, without using Intel DDIO, whenever an application has to write a packet or to generate a packet, it will allocate a specific buffer. If that particular buffer is not available in the cache, that line will be brought from the memory. Then it will generate the data or it will write the packet. Then once the packet is ready, the NIC will take the packet from the cache if it is available in the cache, and then it will send the packet to the over the physical link. But additionally, what will happen is that particular cache line will be evicted to DRAM. So every time, and normally it happens is that the application will write the upcoming packets on the same buffers. So this particular cycle will continue again and again, because every time I have to write into a particular buffer, I will write the packet data and I will then evict that particular line. So this round trip will be there for every packet. But in case with Intel DDIO, they have done two optimizations in this approach. First is that whenever an application has to write the data or generate the packet, that cache line will be allocated in the LLC itself. It will not be brought from the DRAM. So this particular activity will not be there in case of an Intel DDIO. And then the NIC will fetch the data and send it over the network. But this particular eviction will not take place. So advantage is that whenever I am using the same buffers to transmit more and more in packets, that particular address will be always available in the LLC, unless it is evicted due to some other reasons or to make space for some other application. So these two changes are there in case of an IO read or a network transmit. So we can have a IO read with fewer trips to memory, So this is basically the summary that if the line is not present, it is not allocated. If it is an LLC, it stays there. So basically, if I am having LLC hit, the data will be serviced from LLC. If it's a miss, then the data will be fetched from the memory. So here basically if we see, so in this case, so whenever we have to transmit the packet and it is not there in the LLC, the NIC will fetch the packet from DRAM and send it over the media. Now let's look at the IO write part, or basically the incoming network read. So whenever a packet arrives, this we have seen earlier also that it will be DMA'd into the DRAM, and from there it will be brought to cache for further processing. But in the case of DDIO, it will be directly written into the last level cache, from where the CPU will take the data to process the packet. So this memory trip, additional memory trip will be saved in the case of using Intel DDIO. And here also we have two modes of operations. One is write update. So basically the address where we have to write the data, if it's already there in the cache, so it will be LLC hit and the cache line will be overwritten. In the case it is not there, then a allocation of cache line will be done and the data will be written. So there are two modes: write update and write allocate. So now these.
Hari, I have one more doubt. So what was happening before DDIO? I mean, anyway, if you need to process a network packet, in that case, the data need to come from DRAM to LLC, right? That was the previous method, right?
Talking about IO read or write?
Anything.
Network transmit or read?
Yeah, yes, network transfer.
Okay.
My question is that, see, now with DDIO, because you are allocating only two ways in the LLC, right? But previously it was that from DRAM, the data.
Previously it was happening is that I will write it into the memory, and from where when the CPU have to process it. So basically it will DMA the packet into the memory and it will raise an interrupt. So then the CPU will take that address and bring that address into the cache to process the data. But with DDIO, what we are doing is that directly we are writing into the cache. It is not going to the memory. So whenever
I got your point. My question is that, so previously the LLC was not involved, is it? The data was data was written from DRAM to private caches directly. That is my doubt. Was that the case?
Yeah, LLC that depends on the cache hierarchy. It can be there, but it will not be directly written. For example, suppose it is going to DRAM and now we have to fetch the data. It can be there in N1 L2 cache, or to make a space, it can be in the LLC also. But that is after it has been written into the DRAM. So at least we have one cycle where this particular access will be there. One memory write and then memory read will be there.
Yeah, that I understood. So my question is that LLC was not involved earlier, and now the data has to go from LLC to private caches, right?
Yes.
Okay, thank you. Please move on.
No, previously LLC was involved, but only after the first access. After the first access, once the DRAM is DMA'd and then the interrupt is handled, then the CPU will do what it is supposed to do. It's a basic cache hierarchy. So if you want to process any address, so it will go through the same cache hierarchy, L3, L2, L1. But the first access itself will be a miss. It won't be there in the cache. But now with DDIO, even the very first access to that address coming from the CPU will be a hit.
Yeah. Okay. So now, I mean, in the previous case, the data could have been put anywhere in the LLC. I mean, the space in the LLC for
that is.
Yeah, I mean the space was not restricted in the LLC, right? But now that is the case.
Yeah.
Okay.
But as such, sir has told me that very first access in case of Intel DDIO you will get in the LLC. Even if it is limited, if somehow we are using it optimally, then we will get most of the accesses satisfied from the LLC itself, the first access. But in case of without using Intel DDIO, every time first we have to bring the data from the DRAM, then only it will be available in the LLC.
Yeah, so I mean, for the frequent accesses, it might be the case that in the previous version was better than that of the DDIO, right? That might be the case because now with DDIO, there is less space in the LLC. I mean,
No,
there is
it's
restricted
not
space.
about the space. It's 2 ways per set, right? So if your LLC is of 20 MB, you are providing almost 1 MB for network at any
Yeah,
given point
okay.
of time. So yeah, Hari will talk about it. If you demand more IO, then what happens? So yeah.
Okay. Okay, thank you.
Sir, I have a doubt in the IO reads lines.
Yeah, go on. What are you waiting for?
Yes, sir. So IO read, matlab, we are getting the information from the memory to the network, right?
You're
Yes,
asking Hari or me? Hari should answer.
Hari,
yes,
Hari.
yes.
Sir. So
IO
what
read basically it's
the
from the
last
NIC point of view.
hello?
Can you repeat question?
Yeah, what if the element that we require, that we want to give to the IO network, is not there in the last level cache? So it is only there in the DRAM. Then what will we
Then
do?
it will fetch from DRAM.
Okay.
Then it will be the traditional case. Traditionally also it happens. Whenever a NIC is to send the packet over the media, it will first check if it's there in the cache hierarchy, then it will pick up from the cache. Otherwise,
Right.
it will directly DMA from the memory.
Okay, sir. Sir,
That part is
without DDIO, so why is the first step always from DRAM if the memory already exists in last level cache? Can't we just directly?
this. I am just shown an example. That is also a particular case.
Oh,
There can be many possibilities. I have just shown one.
okay, sir. Okay.
So for read path, there are many possibilities, but for the write path, you have to go through DRAM. There is no other way in the conventional IO request handling.
Right, sir.
Yeah.
So till now, whatever I have told, this is also mentioned in the white paper given by Intel. And these now there are also multiple tuning opportunities where we can increase the performance as gained by the Intel DDIO. So and these have been outcome of multiple research papers. So I'm just summarizing. There is one MSR register IIO LLC ways where we can set the number of LLC ways which can be reserved for DDIO. For example, for Skylake, default 2 bits are set, and we have and the authors have done multiple experiments to show that if we increase the number of bits, it basically amounts that we are increasing the number of LLC ways reserved for DDIO and done a number of performance optimizations. So maximum we can set 11 bits, which is the number of LLC ways in the Skylake, and there is also option to disable the DDIO. So now let's look at the result of experiments. So in this paper, in this experiment, they have plotted shown the 99 percentile latency for the increasing number of RS descriptors. So why RS descriptor is important is that it's basically tells the how many buffers are available. So for example, if I say that I have 4096 buffers, so these many number of packets can be under processing the CPU. So number of increasing these RS descriptors is very important if my incoming data or incoming network IO is coming at a higher rate, because somehow I have to store the packet before they are being processed by the CPU. So the result of this is that as we've told that we have 2 LLC ways only. So if I increase the descriptor, so and these descriptors will be stored in the 2 DDIO LLC ways. So as we have seen that incoming data will be written into the LLC way. So if I increase the descriptor, then my space will eventually be filled, and to make space for new data, will have to evict the write. So in that case, my latency or my performance will be degraded. But for example, in here, this light blue line, it is the case of default 2 LLC ways. So here we can see as we go from 256 to 4096, there is a consistent degradation in latency. And if we increase the number of ways to 8, for example here, so here we can see that even if we increase the descriptors from 256 to 2048, I am getting a better or similar latency in comparison to the default configuration. This shows that as somebody also pointed out that although the space is limited, we can tune this allocation so that we can provide a better performance in the case of high-speed network I/O is involved. Similarly, this shows the.
I have a question. So you have said latency. Latency means the packet processing time, or what is this latency?
Latency means end-to-end how much packet how much processing speed we are getting. This is basically they have a setup where they are sending. This is end-to-end latency basically. Like from one server to another server, we are sending the packet, and it is again sent back to the first server. It's a round trip latency. But in the interest of time, I have not shown the complete experiment setup. Latency means that what is the speed we are 99th percentile is how much speed we are getting per packet. It is not the packet access time.
Okay, so input packet is arriving, and then after processing, it is departure. It is getting departed from that other port. So that
basically we have a 2 server setup where we are sending a round trip packet. And this tuning, suppose from server A to server B, I am sending the packet, and again it is going to server A. Then at the server B, we are doing all this tuning. So by measuring the this departure and arrival time, I can find what is the round trip latency for a packet. Okay, then we come out of this figure. This is not the latency when we talk in microarchitecture terms. This is network performance parameter.
Okay, thank you.
This shows the relation between the packet size and RS descriptor. So here we can see if we consider a 1500 bytes packet, this orange line. So we see and we measure the PCI write hit rate. So basically this means that we are getting the packet in the LLC itself. So we can see that as my number of RS descriptors are less, I am getting a better hit rate. And when I increase my number of RS descriptors, I am getting a lesser hit rate. This is because as I increase my number of descriptors, that means I am storing a large amount of data or large amount of packets on the 2 LLC ways, which so that's why this write hit count will be reduced. That I will explain in the next slide. Now the relation between number of cores and DDIO capacity. So here we have done the authors have done an experiment where we measure the PCI write hit rate for different number of DDIO ways. So see, when we want to improve the performance or we want to scale the system, one option is we can increase the number of cores. For example, the green line shows the write hit rate for 2 cores, and red line shows the write hit rate for 4 number of cores. So when we use the default 2 LLC ways, we can see that my write hit rate increases from 40% to around 60% when I increase the number of cores. But if I increase the number of DDIO ways to 4, so using a lesser number of core, I can get a better hit rate. For example, even if I am using 2 cores, here I am getting a hit rate of 80% in comparison to 60% hit rate of 4 cores. So this shows that there is one option. So instead of scaling to multiple number of cores, we can increase the number of DDIO ways. But it also depends on the characteristics of application. So it will be beneficial only when my application is more network I/O. So if it's CPU intensive application, then it will not be beneficial. So now let's talk about 2 performance issues which we discussed earlier also. One is the leaky DMA problem. So this is represented a figure. We have a number of LLC ways. Out of this, 2 LLC ways are reserved for DDI. So whatever the incoming packets will arrive at the NIC, they will be stored in this limited space only. So it may happen that my packets are arriving at a faster rate in comparison to my processing speed. So at one time, for this space will be full, and for making space for newly incoming packets, I will have to evict an existing data to the in memory, and it may be happen that it is an unprocessed packet. So whenever the CPU have to process it, it will again fetch the data or fetch the packet from the main memory to cache. So that was actually earlier pointed out also. So this is happening due to my limited DDIO LLC space available, and this happens when my IO is coming, network IO or the network packets are coming at a faster rate. So why this is a problem is because unnecessary we are having a memory round trip. So unprocessed packet, first we have to store it into the main memory, then again the CPU will process it. So this the authors have termed as a leaky DMA problem. And the solutions they have proposed is buffer sizing. So basically, if somehow we limit the number of buffers or the RS descriptors so that the outstanding number of packets which needs to be processed can be fit into this limited space, then this problem will not occur. But the downside of this solution is that I have a limited number of buffers available. So it will eventually happen that at a high speed packet drops will happen. So this is one issue with this. The second issue is the latent contender problem. So as we know that using Intel CAT, we can the cache allocation technology, we can divide the LLC base into different applications. For example, these are for application 1 and this is for application 2. But it may happen that there is an overlap of DDIO LLC base with the application LLC base. And in that case, it may happen that core to IO eviction will be there. For example, this incoming IO can evict the data which was stored by the core, or if it's a CPU intensive application which is writing the data again and again on the LLC, then that CPU data will evict the data of network data stored by DDI. So this will lead to the resource contention. So these two are issues due to the default behavior of DDIO. And in the papers, they have done a number of experiments, proposed a number of ways, such as we can increase the number of LLC ways, like that we can do. Or for this also, what they have done is, if I know that this particular LLC way is reserved for DDIO, then I will not allocate this way for any particular application. So this kind of tuning and proper placement can be done to resolve these issues. So in summary, we have seen that using Intel DDIO, we can reduce the latency and increase the system IO bandwidth and reduce the round trip of packets between DRAM and cache. And with proper tuning of DDIO, proper placement of the DDIO ways, it is possible to increase the performance. And when we have to scale the application, like my network speed is increasing, right? I have to go from 1 Gbps to say 10 Gbps. Then there are other options available, like instead of going for a multiple number of cores, we can increase the number of LLC reserved to the DDIO. And there are performance issues such as leaky DMA, latent contender, which requires proper tuning of DDIO because of the limited space available. Thank you. Any questions?
Hari, in the case of leaky DMA, I did not completely understand the point. My question is, could you please just briefly give me your viewpoint on that? What is this leaky DMA?
Leaky DMA basically happens is that I have a limited space available for DDI. So I have a 2 MB of space is there, and my packets are arriving at a faster rate. So by default, we know that this packet will be stored in these particular LLC base only, from where the CPU will process the packet. So if the CPU has processed the packet, then that particular packet is evicted, then it's not an issue. But it may happen that the NIC has stored the packet, but it is yet to be processed by the CPU, but it was evicted to make space for newly incoming packet. So now what will happen is that whenever the CPU, because CPU has to process the packet, at that time again the packet will be fetched from DRAM and stored in the cache. So unnecessary so the DDIO like what is the feature of DDIO, like directly we can process the packet from LLC, that is not being utilized fully because unnecessary memory write and memory read is happening. So that is what they call leaky DMA problem. This is happening because of the limited space available to DDIO.
Okay, so my understanding is that you don't want the packet which is not yet processed to be evicted from the LLC, right?
Yes, yes.
And the eviction, so for DDIO also the replacement policy is similar to that of LLC, whatever will be there, right?
Once it is there in DRAM, then it can be placed in any of the LLC way, depending on the replacement policy.
Yeah, I mean what I'm asking is that let's say if a set has two, I mean let's say two ways are allocated to DDMA, right? So then which way, like the data will be evicted from which way will be made, this decision will be made on the basis of replacement policy.
Yes.
So it is safe to say, right, that the replacement policy need to favor the packets which are not yet kicked out from, I'm sorry, which are not yet processed from the CPUs. Like, are you getting my point?
Yeah, there is no such information on the public domain. So right now it's just assumed that the LLC uses the conventional replacement policy, whatever it uses, irrespective of favoring IO request or data request.
Okay. Yeah. So my point was that only, like that this replacement policy will be responsible for this kind of decision.
Yeah, Hari, Shuman.
Hello, I have a question.
Yes.
Okay, you can.
So since it is a hardware-based solution, so what are the performance benefit compared to the RDM-enabled NIC or smart NIC? If we use smart NIC or RDM-enabled NIC, we can do processing in the NIC itself. Then we can save our memory access that you were talking about. So do you have any numbers with that?
The number, I don't have any number of comparison between RDMA and this, but this is applicable to different type of applications.
And I have one more question. Since DPDK is an application-based optimization, so it reduces the user space and kernel space switching. So your solution DDIO, when you measure the latency, DPDK is enabled at the time or not?
This I have taken from the paper. I have not done that, but in that case they have used
Did
DPDK.
they mention in the application center?
They have used DPDK. They have used, I think, test
DPDK with DDIO or DPDK without DDIO?
They have used DPDK based application for this. I think they have used test PMD.
Okay, they have used test PMD. Okay, thank you. So do you know the optimization they have did?
This only I have shown in the paper.
Okay.
So basically, they have run the application and by changing the number of DDIO ways, for example, in this case. So they have run their sample networking application, and they have changed in every run they have changed this number of LLC ways assigned.
Okay, I have a doubt in this graph also, but I will clear with you later.
Okay.
Yeah, so my question was related to the LLC capacity. So you said that for DDIO only two LLC sets are reserved, right? So so can't we like relax that condition and say use a maximum capacity for that particular, like for DDIO packets, instead of fixing the ways we can just use any way and just use a maximum capacity limit for DDIO.
Yeah. So that's what this paper have done. So they have increased the number of LLC ways allotted. This register is there, so where we can change this value to increase the LLC ways. So by default, Intel has kept two LLC ways, and then they have, using the experiments, they have changed the number of LLC. So we can increase the number of the DDIO capacity. For example, if on my server only network IO application is running, in that case it will be beneficial to use more number of LLC ways. And in case if there is a mix of CPU intensive and IO intensive applications, then it will not be benefit, because if I increase the number of LLC ways for DDIO, then it will impact the performance of other CPU intensive applications. So ultimately, it boils down to what kind of applications, what mix of applications we are running on the target server.
Yeah, that is okay. But my point was that say the application is not network friendly, like not friendly for DDIO. So we need the number of LLC ways should be less, which are allotted to DDIO. So instead of fixing the number of ways, we can just use a maximum capacity limit for the DDIO.
So Suman, if you don't need LLC space for IO, you can just disable it, right? That is one way of controlling the LLC space.
Okay.
So if you disable the entire 12 ways or 20 ways will be for CPU processing, the data processing.
No, like my point is like say 10% of the ways are there.
This is just a sweet spot for, given a packet size, given a NIC traffic rate, 2 ways may be good enough sweet spot. Okay.
No,
But if you need more, then you can increase, or if you don't need, you can disable.
No, the current problem with this method, like where the DDIO lines get evicted by application lines. So if we not fix that particular way and we can just make it flexible, then that problem would go away, right? Or
if you make it flexible, how will you track which particular ways are actually for IO ways?
maybe we can just keep type for it.
Yeah, you have to keep an additional bit.
Yes.
Yeah, possible. So this is done by way masking, where you mask 2 ways or the LLC saying that this is for DDIO request, but you can have additional bits per way saying whether it is storing IO request or normal data, right? Possible. These are all open questions. Okay then, thanks Hari. If there are other questions, you can ask Hari directly. So you can stop sharing, and Virendra, you can stop recording.